So our last four modules were all about a t-test, and we're moving on now to a new kind of statistic called an ANOVA. This is an abbreviation that stands for Analysis of Variance, ANOVA. Before we start that, we need to review back from Module 2 what the concept of variance even is. So let's walk through the process again of calculating the standard deviation using the definitional formula. You see here the definitional formula is listed as the sum of all of the deviation scores squared. Remember, a deviation score is how far is a score away from the mean. You square each one to get rid of the negatives and sum them up. So if we have this list of scores here, we would, in order to find the mean, we would first sum them up, which would equal 30, and then we would divide by how many there are. That's 5, so the average is 6. Then the next step is to compute deviation scores. Each deviation score is the distance between the score itself and the mean. So 1 minus 6, negative 5. 9 minus 6, 3. 5 minus 6, negative 1. 8 minus 6, 2. 7 minus 6, 1. After that, we have to square each deviation score. So we take the squared deviation score, which is negative 5 squared, 25. 3 squared, 9. Negative 1 squared, 1. 2 squared, 4. 1 squared, 1. And then, in order to get the sum of those, the sum of the squared deviations, we add up the squared deviations. That comes to 40. Now, before we move on, what's this called? What do we refer to this number as? This is the sum of squares. After we finish computing the sum of squares, if you look up here, let's assume this is a population of scores. So we want to find next the variance of the population of scores. That equals the sum of squares over n. So you take the sum of squares here that we just computed and divide by how many scores there were. There's 5 there, so 40 divided by 5 is 8. Then, in order to finish this formula, remember when we drew an analogy back in Module 2 that was if you want to thread a needle, you blow up the needle really huge, you can shove your whole arm through. You can just grab a fistful of thread and put your arm through, and then when you're finished with that magic trick, you got to shrink the needle back down so that you can use it in sewing your button on or sewing your clothes or whatever. So here, in order to reverse what we did here, this is the standard deviation in squared form. This right here is the standard deviation in squared form. And before we move on again, I'll ask, what's this called? The variance. And what is the variance? It's the mean of the squared deviations, the average of the squared deviations, the average of them. Okay, but it's still in squared form. So in order to reverse that, in order to get it back down to its original form, in its original units, we take the square root of the variance. So the square root of 8 equals 2.83. That said, when we're computing a sample standard deviation, we have to change this value here. This, when we're computing a population, is the n. All the scores that exist. But when we're computing a sample, we have to use what's called the degrees of freedom, which is n minus 1. So if we were computing a sample variance and a sample standard deviation, the sample variance here would be 40 divided by n minus 1. So we have here 5 scores minus 1 is 4. 40 divided by 4 is 10. So then if we wanted to compute the standard deviation for this sample, we would take the square root of this 10, and instead of being the square root of 8 like it was before, the square root of 10 is 3.16. So remember, as you've completed your homework many times now, SS over DF is variance. Sum of squares divided by degrees of freedom is variance. And we, in this chapter, are computing what's called an analysis of variance. So this principle of dividing SS over DF is going to come in a lot within this chapter, within this module. So here's an introduction to the analysis of variance, the ANOVA. The analysis of variance is used to evaluate mean differences between two or more treatments. It uses sample data as a basis for drawing general conclusions about populations. So you can imagine here that we have a population with an unknown mean, from which we draw a sample and we give it treatment 1. We compute its mean, and we want to ask the question, is this population of all the people who've ever received this treatment or ever could receive this treatment different from population 2 who received treatment 2? We don't know their actual mean, but we do draw a sample from them and we compute the sample mean. And population 3 with a different treatment, treatment number 3, and we don't know their mean, but we draw from them a sample and compute their mean. We have to ask the question, is treatment 1 different from treatment 2, and is that different from treatment 3? Are there any differences in these means? So an ANOVA works like an independent measures t-test, where we have, remember, in an independent measures t-test, we would have two populations and we would just compare the sample means for the two populations. But this has a clear advantage over the t-test. It can be used to compare more than two treatments at the same time. So if we have 3 populations, 3 different treatments, we can compare all of them and answer the question, are there any differences anywhere here? But before we move on, we need to establish a little bit of terminology. There's a phrase that's used when we're doing ANOVAs that's called a factor. A factor is the independent variable that designates the groups being compared. This could be a true independent variable or a quasi-independent variable. So a factor is the independent variable. Sometimes there's more than one, but there's always at least one. So if you have gender as your factor, then there are at least 2 groups, male and female. You might also have a third that's like non-binary. And when you have, like what we're talking about there is the, again, is a factor. But that factor has different levels. The levels are the individual conditions or values that make up a factor. So in the case of gender, like I just said, it could have at least 2 levels, male and female, but it might also have a third, non-binary, or you might have some other designations there. A factorial design is a study design that combines 2 or more factors. So if we add this IAL at the end of the word, then that means we've used more than one factor, more than one independent variable. Let me show you an example. This is what the structure of an independent samples or between subjects t-test looks like. You might have 2 conditions, no music and rap music. You would measure people's test scores after listening to no music while they study, or measure their test scores after listening to rap music while they study. And you'd have some 30 people in one group and maybe 29 or so in another group. A single factor ANOVA would add a third condition. So you might have some people listen to classical music in addition to your other 2 levels. You would then measure the test scores of those people who listen to classical music, and you would compare the 3 groups to each other to see if there are any differences anywhere among the 3 groups. But this is a single factor because there's only one independent variable, and that's music type. And the levels of that factor are no music, rap music, and classical music. let's work through this example. Here we have a therapy technique. We might have a first group and a second group that have two different kinds of therapy. One might be, I don't know, behavioral therapy, and another one might be like cognitive behavioral therapy. Then we have a time series as a second factor. And here we would say we've got before therapy, after therapy, and 6 months after therapy. And in each one of these cells, you would have some scores on some dependent variable that you're interested in. They would be scores for this group 1 that's measured before therapy, and scores for this group 2 that's measured before therapy. And group 1 measured after therapy, group 1 measured 6 months after therapy, and so on. So my question for you is this. How many factors would there be in a situation like this, where you've got 2 different types of therapy, and you measured them at 3 time points? Hopefully you said there were 2 factors. This is the first factor. This is the second factor. My next question is, how many levels in each factor? Hopefully you noticed that there are 2 levels in the first factor and 3 levels in the second factor. So let me ask this question. Is this a factorial design? You should say yes, because remember, if we use multiple factors, right here we have 1, 2 factors. If we use multiple factors, then we add this IAL at the end and we refer to it as a factorial design, meaning more than one independent variable, more than one factor. Are there any independent measures here? Remember back to our t-test modules when we learned about what independent measures were. They're groups that are separate from each other, not the same people. Are there any independent measures or independent factors? What about any repeated measures or any repeated factors? Hopefully you noticed that therapy technique was an independent measure. These are separate groups of people receiving 2 different kinds of therapy. But time is a repeated measure because we have the same group of people before therapy as after therapy and then 6 months follow-up. So here we've got a repeated measure. We're tracking them over time. Group 1 versus group 2. Those are independent measures. Now, in this module, we're only going to be evaluating single factor ANOVAs with independent measures. So we're not going to deal with these kinds of really complex designs here with multiple factors. We're not doing anything factorial in this module, and we're not going to do anything repeated in this module. We're just going to use independent measures on a single factor ANOVA. In future modules, we are going to cover concepts surrounding repeated measures ANOVAs and factorial ANOVAs, so that's the reason why I wanted to introduce this idea here now. But for now, we're just going to stick to our single factor ANOVAs where we just have one independent variable, and it might have 3 levels, which means 3 conditions, or 4 levels, like that, 4 conditions. Or it could have 5 or 6. It could have as many levels as we want, but they all have to be along one dimension, like music type or therapy type or gender or something like that. Okay, so when you're running an ANOVA, you have to write out your statistical hypotheses, just like we've been doing for the last several modules. The null hypothesis is that the level or value on the factor does not affect the dependent variable. So whichever condition or level you're in doesn't have any impact on the dependent variable. So in the population, this is equivalent to saying that the means of the groups do not differ from each other. So if you had treatment 1 and treatment 2 and treatment 3, their means, the means of those populations would be equal to each other. So all 3 means of all 3 different populations are the same if the null hypothesis is true and the treatments don't work. But the alternative hypothesis can't be written in a statistical notation with these symbols like we've been doing, because there are too many ways in which the null hypothesis can be violated. Look down here. Under what circumstances can the null be wrong? Well, it could be if all the means are different from every other mean, or it could be if some of the means are not different from some of the others, but other means do differ from some means. And so instead of writing this out in some kind of statistical format, we have to write in words something like, there is at least one mean difference among the populations. So we would violate the null hypothesis if mean 1 and mean 2 were the same, but mean 3 were different. Or if mean 1 and mean 2 were different, but mean 3 was the same as mean 1. Something like that. The test statistic for an ANOVA follows this format down here. But in order to make sense of that, I want to remind you first that the overall structure of a t-test that we've been doing for the last several modules looked like this. We took the obtained difference between two sample means. That might be, like, remember the independent samples t-test was when we took two sample means. Other t-tests were if we took like the same sample and repeated it, or if we took one sample and compared it to the population. But the point here is that we had a difference that we obtained in actual units. So one sample might be a mean of 5, and another sample might be a mean of 10. And the difference between those two, between 5 and 10, is 5 units. That's the obtained difference. And we divided that by the standard error, which was defined as the difference that we would expect between any two sample means at random if there was no treatment effect, if the null hypothesis were true. And so we would take that difference we obtained, like let's say it was 5, like we just talked about, and we would divide it by how big a difference we would expect there to be just by chance. And if that was a small difference, like 1, then we would say, whoa, that's a really big t. 5 divided by 1 is really big. But if the difference that we would expect just by chance is very large, like 10, then we would say 5 divided by 10 is only a half, 0.5, and that's a very small t that would fall right in the middle of the distribution. And so what we're doing here when we compute the t, if you recall, is comparing the size of the difference that we saw divided by the size of the difference we would expect to see if the null hypothesis were true and the treatment didn't work, just by chance. Okay, so an F ratio is actually very similar to that. It's just based on variance instead of sample mean differences. But we still take the differences, or the variance. Remember, variance is the differences, the size of the differences that we see in scores. So we take the variance or the differences that are between sample means, and we divide it by or compare it to the variance that we would expect if there were no treatment effect, if the null hypothesis were true, if the treatment didn't work. So the differences that we would expect to find just by chance. So we compare how big a difference we saw versus how big a difference we would expect to find just by chance if the null hypothesis were true and the treatment didn't really work. So this fraction that we were computing here for our F statistic, sorry, I forgot to say, an F is an abbreviation for ANOVA. You could call it an F test just as well as you could call it an ANOVA. Anyway, this fraction that we compute for our F is the same idea as the fraction we computed for our T. So we're just doing the same thing here that we've been doing for a long time. Now, one might wonder why we compare the variances in the F fraction or the F ratio instead of sample mean differences like we did with the t-test. Well, the answer is that it's not possible to compute a sample mean difference between more than two samples. So for example, you might say, how much difference is there between 10 and 15? Well, it's easy, right? It's 5 points. That's a 5-point difference. But if you ask the question instead between 3 conditions, how much difference is there between 10 and 15 and 21? Ooh, that's not a possible question to answer. You can answer the difference between 10 and 15, or 10 and 21, or 15 and 21, but you can't answer as one question, what's the difference between 10 and 15 and 21? And so, instead of using the mean difference like we did in the t-test, just comparing 2 conditions, we have to compare the variance or the variability across these three conditions when we run an ANOVA. So let's talk about this, the test statistic that is an ANOVA. This F ratio is based on variance instead of the sample mean difference. The variance that's used to define and measure the size of the differences among the sample means is the numerator. And why do we use variance? Well, I've just described in the last slide that we have to use something other than the sample mean difference. So why do we choose variance? Because if you look at set 1 right here, you've got 3 different means. Let's say that these are treatment 1, treatment 2, treatment 3, and we've computed the mean for those 3 groups. Those 3 means are quite different from each other, 20 and 30 and 35. And if you compute the variance, S squared variance, for those 3 groups, you would get 58.33. Set 2 has 3 other imaginary treatments, 1, 2, and 3, but their means are much closer together, 28, 30, and 31. You can see how close they are together. The variance of those 3 means is much smaller, 2.33. So notice that the sample means in set 1 are far apart, right here, and their variance reflects that. See how large this variance is? So variance is a good measure of the size of the distance between sample means. So since we can't answer the question, what's the difference between 20 and 30 and 35, we can say instead, what size is the variance between these sample means? And here we have a large number to reflect large differences. And we could say, what's the variance between these sample means? And you have a small number to reflect small differences. Variance in the denominator of the fraction, underneath at the bottom of the F ratio, measures the mean differences that would be expected if there is no treatment effect, the size that you would expect just by chance. So going back up here, remember the variance in the numerator is defined as the measure of the size of the differences among the sample means. So we see the size of the difference that we do observe, and we divide it by how much we would expect to find if there was no treatment effect just by chance. Sometimes students wonder why we don't just repeat multiple t-tests. If we can compare population 1 versus population 2 and population 1 versus population 3 like this comparison, and then population 1 versus population 3 like this, why don't we just run 3 different t-tests in order to compare these differences and see which ones are different from each other? Well, the answer lies in type 1 error rates and how it's related to multiple hypothesis tests. Experiments often require multiple hypothesis tests, each one with a type 1 error. This is called test-wise alpha. Now, when you run the first t-test of those 3 that we just talked about on the last slide, that has an alpha of whatever you've chosen. Let's say it's 0.05, because that's conventional. If the alpha size is 0.05 for each of those tests, and you run 3 of them, your alpha would be 0.05 for the first one, 0.05 for the second one, and 0.05 for the third one. You would have to add those together for an alpha of 0.15. And remember that each one of these represents the probability that you've made a type 1 error to say, there's an effect, this treatment worked, when really it didn't. This represents a huge increase in the probability of making a type 1 error. So instead of being wrong every 5 out of 100, you'd be wrong every 15 out of 100, or 15% of the time. ANOVA allows us to evaluate all the mean differences simultaneously with just one test, regardless of the number of means. Even if there was 10 different populations we were comparing, we could compare all 10 populations to each other and see if there are any differences among any of those populations. And thereby we would avoid the problem of inflated experiment-wise alpha, because the ANOVA has one alpha level. If we choose it at 0.05 and we run the one ANOVA test, then the probability of making an error on that one test is just the alpha, 0.05, whatever we set our alpha at. So this isn't associated with this same problem of multiple t-tests adding together the alpha level of each one and causing an inflation in our error rates. Now, I've kind of hinted at this a couple of times, but we might answer the question, why is it called analysis of variance? Notice that these scores are all different. Here we have a first treatment that is some people who don't use a phone, a second treatment that has a handheld phone, and a third treatment that has a hands-free phone while driving a car. And these people are in a driving simulator, and we want to know how many, how well their performance is. So let's say that high scores mean good performance. We would see that the average of these people who don't use a phone is about 4 high performance compared to people who have a handheld phone or a hands-free phone, which both have a mean score of driving performance at 1. But these scores are all different. Somebody got a 4 here, somebody got a 3. Another person was in this driving simulator and got a 1. Another person over here was in the same driving simulator but used a hands-free phone and they got a 0. And this person got a 0 and a 1. They're all different from each other. In other words, they vary. Our goal is to measure the amount of variability, how much they differ. First, we measure the total amount of variance or variability, the total amount of differences between all of these different scores. Then we separate it into smaller parts. Hence, we're analyzing the variance. Hence, analysis of variance, ANOVA. We're analyzing the differences, the variability, the variance of all these scores. Now, there's multiple sources of variability here at play. There are especially, in particular, 2 main sources of variance, or of differences in the scores. The first one is between treatments, and the second one is within treatments. Between treatments refers to the differences between Group 1 and Group 2, between Group 1 and Group 3, between Group 2 and Group 3. Between treatments. There are 2 sources of variance when we analyze between treatments. Systematic differences caused by the treatments themselves, and random unsystematic differences that are just due to measurement error and individual differences. So let's look at that. The first one, systematic differences caused by the treatments. Some of these scores are much better than some of these scores. Not all of them, mind you, because look, one person here got a 3, one person here got a 3. But on average, these scores are higher than these scores and these scores. There are systematic differences that are caused by the treatments. The difference between 4 and 0 or 4 and 1 or 4 and 3 is in part due to the fact that this guy here, we'll call him Joe. Joe has more experience driving than, say, Susan, who's here, or maybe Sally. But part of the reason also is because he is not using a phone. The systematic differences are the parts that are caused by the fact that he's not using a phone. But the random differences that are unsystematic are due to the fact that Joe has some experience driving that Jill or Sue don't have. But some of the people here in this group will have less experience driving than some of the people here in this group. Some of them will have woken up on the wrong side of the bed. Some of them won't have had breakfast, and some will. Some will have arrived late at the driving simulation experiment, and some will have Some will just be a little shorter than others, and they won't be able to reach the pedals as well. And there's just all kinds of random differences between all of these different scores. And those random unsystematic differences contribute to the differences here that we see. But we also see that some of the differences are due to these systematic differences that are caused by some people not using a phone, some people using a handheld phone, and some people using a hands-free phone. There are no systematic differences within each group. At least if you've designed your experiment well, you hope there aren't any. So there's only one source of variance within treatments. That is, if we take one of these treatments and look within it, inside of it, within the treatment, there are differences. 4 is not the same as 3. Joe is not the same as Bob, and Bob is not the same as Suzette, and Suzette is not the same as I don't know. Anyway, these people are not the same as each other. These differences are not due to any treatment effect, though. They're just due to random, unsystematic differences that are because of measurement error and individual differences. Okay, we have to demonstrate that any observed differences that we see in the groups are greater than what would be expected by measurement error alone. So, any differences that we see here between 4 and 1 and 1, we have to demonstrate that that difference of 3 points here and of 3 points here and of 0 points here, that those differences are greater than what we would expect just because of random differences across groups within each group, the random differences across individuals within each group. In order to do that, we take the total variability and we split it into these two parts, the between treatments variance and the within treatments variance. Just like we talked about on the last slide, between treatments variance are those differences that are between the conditions, the difference between 4 and 1 and 1. But those differences can be chalked up to two sources of variability. One is the systematic differences because of treatments, like which kind of phone do you use, and the other source is because of random individual differences and unsystematic factors. When you look at the within subjects treatments, within each condition, within each group, you look at the source of variability inside that group and see that there are only differences because of random unsystematic factors. If we compare these two things against each other, the differences including any treatment effects, the differences both because of randomness and because of systematic treatments that include any treatment effects, and we divide it by the differences with no treatment effects, right here, the differences that we just find randomly by chance without a treatment effect, then we get our F statistic. Another way of saying that would be to say we could take the F being equal to between treatments variance here and dividing it over within treatments variance here. You could also say instead that the F statistic is the systematic treatment effects plus random unsystematic differences. And we divide that by the random unsystematic differences. So it's both of these combined divided by just the one alone. However you think about it, what we're doing here is we're saying that we're trying to take the systematic treatment effects, the size of the differences because of the treatment, and the size of the differences because of just random individual differences, and divide it by how much difference we would expect there to be just by chance because of randomness. Let's take that definition of the ANOVA, the F ratio, and talk about the numerator and the denominator. The denominator of the F ratio is called the error term. This denominator is called the error term because it's an estimate of the error variance, or the variance that's just due to random stuff. Remember, in statistics, the word error is the stuff that we haven't accounted for. It's not a mistake that we've made. It's just stuff that we haven't accounted for. In this case, it would be the differences between individuals just because of having woken up at different times in the morning and arrived at different times at the shop, and some people being more frazzled, and some people being taller, and some people being shorter, and some people eating breakfast, and some people not, and some people have more driving experience, and whatever. All those individual differences we chalk it up to error. It's stuff that we haven't measured. So in the bottom, we call that error. In the top, we call this the treatment effect plus the error. If the null hypothesis is true, then the size of the treatment effect is near zero because the treatment didn't work. There is no difference because of the treatment. The treatment is nada, null, nothing. There is no treatment effect if the null is true. If that were the case, then we would have an approximate estimation of the degree of error divided by the degree of error, because the treatment effect would be nothing. Error over error is near 1, because let's imagine what error values we could have here. If the degree of error in this experiment were 3, and we put it here and we divide it by 3, 3 over 3 is 1. If it was 10 over 10, it'd be 1. 8 over 8, 1. Whatever it is, whatever the degree of error is, over itself, it should be about 1. Now, it's not always going to be exactly 1 because error is error. It's going to be variable. It's going to just be slightly different. So the differences that we see between our groups are just going to have like a little bit different of differences than the differences that we see within each group. And so it's not really ever going to be exactly 1, but it's going to be something close to 1 if the null hypothesis is true. But if the alternative hypothesis is true, then the size of the treatment effect is more than 0. It's some value here. And if we take this value and we add it to the error and we divide by the error, then this should be noticeably larger than 1. So let's say the error was 3. We plug in 3 here for the error and 3 here for the error, but our treatment effect was a size of like 10. That would be 13 divided by 3, something much larger than 1. Before we move on, we need to talk about some ANOVA notation. Here in this table, we have the same scores that I showed you before. These are the no phone group, the handheld phone group, and the hands-free phone group. But we have here a bunch of letters underneath and a bunch of computed values and some off to the side here. Because ANOVA involves a lot of calculations, I'm going to explain to you what these letters represent. First, the little n in this situation means the number of scores in each treatment. Like N1 or N2, you put a little sub next to the treatment number. So this is treatment 1, so all of these have here a sub 1. This is treatment 2, so they all have a sub 2. But N is the number of scores inside this treatment. So here there's 5 scores. Little n equals 5. K represents the number of treatment conditions. You can see here we have treatment 1, treatment 2, treatment 3, so K is 3. The total number of scores is a capital N. I know in a previous module that we talked about capital N representing the number of scores in a population, but here in this module we're going to change the definition of capital N. Capital N in the scientific literature doesn't always mean the number of a population anyway. Oftentimes when you see a published paper, they'll use a capital N to represent their sample size in that paper. There's not a uniform convention for the letters that we use in statistics, not all the time. So in ANOVA, in this chapter, or in this module, I'm going to use capital N to represent the number of scores in the whole experiment. That is 5 plus 5 plus 5. So you might have noticed that if all the samples are the same size, like they're all 5 here, then the big N is equal to the little n times the number of conditions. So 5 times 3. But if they're not the same, then you can just add up how many there are in each condition, and that's the total n size. T represents the sum of the scores for each treatment. So the sum of X for each treatment. If you add up 4 plus 3 plus 6 plus 3 plus 4, that comes to 20. If you add up 0 and 1 and 3 and 1 and 0, that comes to 5. So the T for each condition is the total sum of the scores for that condition. G represents the grand total of all the scores in the study. So if you take the sum of your individual T's right here, then that will add up to your grand total. But you can also just take 4 plus 3 plus 6 plus 3 plus 4 plus 0 plus 1 plus 3 plus 1 plus 0 plus whatever these are. Final note here, there is no universal notation for ANOVA, just like there's no universal notation for most of what we do in statistics. These are the letters that we're going to use in this class, but other sources might use other symbols. So don't memorize these and think that they're always going to be universally used in every class that you might take on statistics. This is just what we're going to use for convention here in this course. Now, let's do a self-check. I'm going to ask you, how do you get each one of these kinds of things? And I want you to compute it. So pause your video after I ask you one of these questions, and then we'll answer it together, and you can test your knowledge. So first, how do I get T? T is the total for each condition. So you would add up these scores for the first, these scores for the second, and these scores for the third. How do I get the sum of squares? Remember, the sum of squares is the sum of the squared deviations from the mean. So you'd take the mean of this group right here, and you would subtract from it you'd subtract from each score the mean of the set of scores. You'd square that deviation, and then you'd add them all up. That would be how you get the sum of squares. How do I get little n? Little n is the number in each condition. So n1 is 5, n2 is 5, n3 is 5. How do I get m? Remember, this italicized m represents the mean. Hopefully you remember that you add up all the scores and divide by how many there are. How do I get the sum of x squared? That would be to take each of these scores and square it, and then sum them all up. So in this case, you get 106, because if you took 4 and squared it, and 3 and squared it, and all those, and squared these, and added up the sum of all of those, you'd get 106. How do I get G? Remember, G is the grand total of all the scores, so you just add up these, and these, and these, or you can add up these, and these, and these, because the sum of the T's is also equal to the G. How do I get capital N? Hopefully remember that this is the number of scores in the entire study. So capital N here is 15. And how do I get K? It's the number of conditions in your study. So there's 3 conditions, which means there's 3 Ks. All right. An ANOVA calculation follows a series of 9 steps. The first one is to figure out the sum of squares total, then the sum of squares between, and the sum of squares within. Just like I explained before, you take the variability and you split it into 2 parts. Here, step 4, you figure out the degrees of freedom total, and then you split it into 2 parts, the degrees of freedom between and the degrees of freedom within. After you finish those first 6 steps, then you compute the variance between treatments, which is the sum of squares between divided by the degrees of freedom between. Remember, variance is SS over DF. So we're computing the variance between by restricting ourselves to the variance, the sum of squares between, and the degrees of freedom between, and putting those in a fraction. Step 8 is to take the variance within treatments, SS over DF for within. So you take this SS within and this degrees of freedom within, and you pit them against each other, and you get this variance within. And then finally, your step 9 is to take the variance between treatments and divide it, like we said before, by the variance within treatments, which represents the variability you see because of the treatments and error, divided by the variability you expect just by chance because of error alone. So, step 1, we have to partition the sum of squares for independent measures ANOVA. First, we compute the total sum of squares. The formula for that is the sum of x squared minus g squared over n. You might say this looks familiar. It should, because it's basically the sum of squares formula that we've been using all along, with g replacing the sum of x here. Then you take the sum of squares total and partition it into two parts: the sum of squares between treatments and the sum of squares within treatments. A formula is given here for the sum of squares between treatments. Students often get confused here, so I beg you, please pay attention to this. The sum of t squared over n represents the t for each condition squared divided by the n for that condition that you took the t. After you figure out that for each condition, then you sum them up and then subtract this component of the equation. So if you have 3 conditions, then you'll have this part here plus another part here plus a third part here, and sum them up and then finally subtract g squared over n. The sum of squares within treatments is the sum of squares that you find inside each treatment added up. So if the sum of squares for the first treatment and the sum of squares for the second treatment and the sum of squares for the third treatment were added together, then you would get the sum of squares within. So let's work through an example. Here we've got our same condition that we talked about before, our same experiment, where we have no phone, a handheld phone, and a hands-free phone. In order to compute the sum of squared total, we follow this formula. That's the sum of x squared minus g squared over big N. If we plug in these values, the sum of x squared is 106. We put that right here. For g, we find 30, and we put it right here. And for big N, we have that here, and we put it there. So 106 minus 30 squared over 15, and that equals 46. The sum of squares within treatments is adding up the sum of squares for each of the inside treatments. So if you take the sum of squares here, and the sum of squares here, and the sum of squares here, and add them together, that's the sum of squares within. The sum of squares between is the sum of all of these components for each condition minus g squared over n. So the t squared over n, remember, is the first t squared divided by n, and then the second t squared divided by n, and the third t squared divided by n, and then you sum those up. So 20 squared over 5, 5 squared over 5, 5 squared over 5, add those up, and then finally subtract g squared over n, which is g here, 30 squared divided by 15, that n right there. So if you carry that through, you've got 80 plus 5 plus 5 minus 60. That equals 30. Notice that the sum of squares within and the sum of squares between add up to the sum of squares total. 16 plus 30 is 46. That will always be the case because when you figure out the sum of squares total, what you're doing is dividing it into two kinds of variability. The sum of squares that's within each treatment and the sum of squares that's between all the treatments. Alright, the next thing that we need to do is partition the degrees of freedom. You take the degrees of freedom total by computing big N minus 1. The degrees of freedom between treatments are k minus 1, the number of conditions minus 1. And the degrees of freedom within treatments is the sum of the n for each group minus 1. You can also compute big N minus k, and it gives you the same thing. But to me it makes better sense to do the sum of the n for each group minus 1 in each of those cases. I'll show you both in the next slide. So degrees of freedom total equals big N minus 1. That's big N 15 minus 1 is 14. Degrees of freedom total is 14. The degrees of freedom within, by one computation, is big N minus k. 15 minus 3 is 12. By another computation, it would be little n minus 1 for each condition added up. So 5 minus 1 is 4, 5 minus 1 is 4, 5 minus 1 is 4, and add the 4 plus 4 plus 4 is also 12. The degrees of freedom between is computed as k minus 1, the number of conditions minus 1. So 3 minus 1 is 2. Notice here again that the degrees of freedom within and between add up to the degrees of freedom total. 12 plus 2 is 14. And that's because when we take the degrees of freedom total, we're splitting it into two different sources of variability, within and between. Woo! It's party time! We finished steps 1 through 6! Booyah! You thought that was going to be much harder, didn't you? Yeah, well, it's not that hard. Here we finished 1, 2, 3, 4, 5, 6. All we have left is 7, 8, and 9. So the next step is to compute the variance between treatments and the variance within treatments. Remember, as I said before, variance is SS over DF. You've written that in your homework so many times now, you couldn't possibly be confused by that, right? Variance is the sum of squares over the degrees of freedom. It's a fraction that represents the amount of variability still in its squared form. In ANOVA, it's customary to use the term mean square, however, instead of variance, or we abbreviate it simply MS, in place of the term variance. Why? Because, as I said at the very beginning of this presentation today, variance is the mean of the squared deviations. It's the average squared deviation. It's the average amount of variability still in its squared form. So just like SS stands for sum of squared deviations, MS stands for the mean of squared deviations. So I know that I've drilled and drilled and drilled and hammered and hammered and hammered into you that SS over DF is variance, but now I'm going to tell you SS over DF is mean squares. It's the same thing. Mean squares means variance. It's the same thing. We're just going to call variance mean squares instead of variance for the length of this module. So remember that variance, or mean squares, is calculated as SS over DF. Therefore, if we want to figure out the mean squares between, or the variance between, then we take SS over DF for the betweens. And if we want to compute the mean squares within, or the variance within, then we take SS over DF for the withins. I've listed up here all the things we previously computed in our first 6 steps, so you should be able to take SS between 30 and divide it by the degrees of freedom between 2 and yield a mean squares between, or variance between, of 15. In order to get the MS within, you should take the sum of squares within, 16, and divide it by the degrees of freedom within, 12. You should find that that mean squares within, or variance within, is 1.33. Okay, now we've finished steps 7 and 8. We finished the SS over DF between and SS over DF within, so we know our variance fraction, and all we have to do is pit them against each other now in step 9. So to compute the F, the final step, we take the variance between, or as we're calling it now, the mean squares between, and we divide it by the variance within, or the mean squares within. We just computed both of those on a previous slide, and we pit them against each other by putting 15 over 1.33, and we get an F ratio of 11.28. Our F, our ANOVA, is 11.28. When you use a computer to calculate your statistics, you'll see your results placed in an ANOVA summary table like this. I recommend you start with a blank summary table and fill in the values as you compute them. This will keep you on track to help you avoid getting lost. So notice that we have the word source here to represent the type of variability that's between treatments and within treatments versus total. And you can say, you can compute the SS and the DF and the mean squares. And you remember we did this as step 1, I think it was 1, 2, and 3, or 1, 2, and 3, it doesn't matter, but this is the first 3 steps, second 3 steps, steps 7 and 8, and step 9. If you write out your table like this, then you will know that you need to fill out these 9 pieces of information in that order like that. Now, I haven't explained to you how we use an ANOVA in a hypothesis test or how we interpret the ANOVA when it's finished. But before we go on, I really strongly want you to pause the video and practice going through a scenario computing the ANOVA, all 9 steps. Use your formula sheet where I've listed out the formulas for all your sum of squares and all your degrees of freedom and your variability, your mean squares, and your F ratio. And you should be able to use this information. I haven't given you the scores because you don't need them here when I've given you all this information so far. Okay, if you have all this information, you don't need the scores. But you should be able to figure out, based on this information, for treatment 1, treatment 2, and treatment 3, your F ratio. That's your goal. So pause the video and figure out your ANOVA, your F ratio, using those 9 steps. Okay, hopefully you found that these were your answers. If you used your ANOVA summary table, it will have kept you on track. Check your answers there and move on when you're ready.